Hi everyone, welcome back. This is our last set of notes for this unit, and in this video I want to go over Dalton's law of partial pressures and the mole fraction. And then in the next video I will cover on collecting gases by water displacement and Graham's law. So let's start with Dalton's law of partial pressure. Now all the original gas laws that you learned before, Charles, Boyle, Avogadro, Gay-Lussac's, and even the combined ideal gas laws, those were all based on observations of air. Now, as you might know already, air is the mixture of several gases, but most of it is comprised of nitrogen and oxygen gas. So Dalton, John Dalton, an English chemist, he figured that a mixture of gases also obeys the same gas law just as a pure substance would, because each gas in that mixture behaves as though it was the only gas present and there's like no other gas is within that container. So he comes up with what he calls the Dalton's law of partial pressures, and it says that in a mixture of unreacting gases, the total pressure is just the sum of the partial pressures of the individual gases, because each individual gas behave as though they're just there by themselves. So the total pressure will just be the sum of the pressure of each of those gases. So then we have our little equation. Total pressure is equal to pressure of each gas added together. And this is what the equation would look like. So depending on how many gases you have in the container, this can go up to like P100, right? You have 100 types of gases in there. But for our purpose, we're probably going to have just like 1, 2 or 3 or just 4. So if you take a look at this little picture here, when you put all of those gases together in one container, the pressure for the total, so that's what it says right here, total, the total pressure for gas A, gas B, and gas C is just the pressure of A plus the pressure of B plus the pressure of C. And this pressure does not change from when they were beginning. So before they join together, so for example, gas B, before it comes into the same container as A and C, the pressure is PB, and it stays PB when it's combined with the other two gases. So that's how we get the law of partial pressures. Another example of partial pressure. So here I have gas A, which is the pressure of gas A is 300 millimeter mercury, and then gas B, here I have it's 400 millimeter mercury. And after you combine both gas A and B and put them together in the same tank, the total pressure comes out to be 700, and that's just because 300 from A and 400 from B, and you get 700 millimeter mercury. So the important thing for you to remember or to understand is that partial pressure depends on the number of moles of a gas and not its identity. So for example, if you have a tank and it's basically the pressure is 3 atmosphere, if half the moles of that tank is helium, then what is the partial pressure of helium? Now the answer is that if half the moles of the gas are helium, then it is responsible for half the pressure, because of this. Partial pressure depends only on the number of moles. So if half the mole in that tank is helium, then the pressure of helium is half the pressure of that container. So, and I know that the container is 3 atmosphere, so then the partial pressure, or the pressure of just helium, is 1.5 atm, which is basically just 3 divided by 2. This is a problem that you're probably going to encounter on your worksheet as well as on the test and exam. Aside from that, the 2 other main types of partial pressure problems that you are responsible for is one is when you have all the individual gas pressures are given, and the second type is when you have the percentages of the gases are given. So let's go over type number 1, where all the individual gases, the gas pressures are given. So here I have a oxygen, argon, helium gas mixture. And so this mixture has 3 different gases, and the total pressure comes out to be 550 millimeter mercury. So first I'm just going to say, okay, I have oxygen, I have argon and I have helium, and that's my total gases in that container. Now, they giving us if the partial pressure of argon is 120 millimeter mercury and the partial pressure of helium is 210 millimeter mercury, what is the partial pressure of oxygen gas? So when it says partial pressure, this terminology just means that the pressure of a particular gas in a mixture. So partial pressure of argon is PAR, and we denote it just like this, P with the subscript AR. And partial pressure of helium, so that's P subscript helium, and then same thing with O2. Now I know that because of the Dalton's law of partial pressures, I know that pressure of O2 plus pressure of argon plus pressure of helium equals to pressure of the total pressure. And I have already been given the total pressure. So all that's left here is for you to basically rearrange this equation a little bit and plug in the numbers. So I'm going to rearrange the equation to solve for pressure of O2 because that's what they're asking me. And then that will become the total pressure minus the pressure of argon and the pressure of helium. And when you plug in your number, you should get this answer. And I'm going to box that because that's my final answer. Type number 2 is when the percentages of the gases are given to you. So let's look at this problem. You have here a tank that is pressurized to 3 atm. Now, if 30% of the moles are helium, 60% are xenon, and 10% are argon, then what are the partial pressures? Because we have 3 different chemicals here, number 1, helium, number 2, xenon, and number 3, argon, you will want to have 3 different answers for your final answer. So you need to box 3 of them. So let's go ahead and do this problem. Remember that the pressure is only depending on the number of moles. So because of that, if 30% of the moles are helium, that means that 30% of the total pressure in that tank is helium. So in order to find the partial pressure, all I'm going to do is to find how much is 30% of the total pressure. In order to do that, I am going to multiply 30% by the total pressure, which is 3 atm, and that should give me 0.8 atm, and that is my answer for partial pressure of helium. Now, then let's do the same thing for the other 2, because remember, we need 3 different answers. So let's do partial pressure of xenon, and xenon is 60% of the moles are xenon, meaning that 60% of the total pressure is the pressure of xenon. So to find that out, I'm just going to multiply 3 atm, which is the total pressure, by 60%. That should give me this number, which is the pressure of xenon. I'm going to do the same thing last for argon, because knowing that argon takes up 10%, or the pressure of argon takes up 10% of the total pressure, I find out the partial pressure for argon by multiplying 10%, which is 0.1, by the total pressure, giving me this number. Now, there's one way for you to figure out whether your calculations are correct is to add them all up. So add all the partial pressure up, and if they equals to the total pressure that was given to you in the beginning, your calculations are correct. Let's go ahead and go over mole fraction. And mole fraction is the concentration of any individual component in a gas mixture, and it's denoted by this italicized X. So it's basically the number of moles of the component divided by the total number of moles in the mixture. So what that means is, so this is the mole fraction. So let's say this is chemical 1. And this is just a general formula. So this is a total number of moles right here in the denominator. This can go on and on and on and on, but that's why we have the dot here. But in your case, you're probably going to find yourself like probably 3 or less. So if this is a mole fraction of, say, chemical 1 out of 3, N1 is the number of mole of that chemical 1, and then you're going to divide that by the total number of moles that's present in the mixture, and that would give you the mole fraction. So keep in mind the mole fraction has no units. So you should not be writing mole as a unit for mole fraction. The mole fraction is because it's mole on the top and mole at the bottom. The mole cancels out, so you end up with no unit for mole fraction. Now, since N is equal to PV over RT, and that's from my ideal gas law, you can actually do a little manipulation of this equation. So N1 would equals, from N1 from up here, would equals to P1 times V over RT, and then N total, here, the total moles of the mixture would equal to P total times V over RT. And when you plug it in like this, you can see that V over RT actually cancels out. And what you're left with is P1 over P total is equal to the mole fraction of 1, so X1. And this, when you rearrange it, gives you P1 equals to X1 times P total. Now, P1 is the partial pressure of chemical 1. And so that can give you, this is a nice formula for you to know and to memorize to solve different types of problems. So this example problem will utilize what we just learned from the last slide, which is the mole fraction. So here I was given a mixture consisting of 7 grams of carbon monoxide and 10 grams of SO2. And this mixture has a pressure of 0.33 atm when placed in a sealed container. What is the partial pressure of carbon monoxide in this container? Remember that the mole fraction was designed for you to figure out the partial pressure because it's based on the mole fraction of that particular chemical. So, and the partial pressure is just the pressure of some particular chemical within a big mixture. So that's a hint for you to find how to use the mole fraction. So step number 1, since we're using mole fraction, we just find the moles. And we can find the moles of each chemical by just using the molar mass. After you've done this part by using the molar mass, you can move on to step number 2. Then you can calculate the mole fraction for just carbon monoxide, which is CO. And you can apply the equation that was in the last slide, giving you this. So the mole fraction of CO is equal to the mole of CO, which is what you just found up here, over the total number of moles. And that is just simply the moles of CO plus the mole of SO2. And after you divide that, you get this number with no unit. Then step number 3 is for you to apply the equation that was boxed in the last slide to find the partial pressure of carbon monoxide. And all you're going to do is you plug it in. So the partial pressure of carbon monoxide is equal to mole fraction of carbon monoxide multiplied by the total pressure. And these two numbers you already know. This one you found from here. So after you did that calculation, you will get this number for your partial pressure of carbon monoxide. You can actually do the exact same step, just switch the numbers out a little bit, if it asks you for what is the partial pressure of SO2 instead. And in fact, that's actually one of the questions in your worksheet. So go ahead and try that out and see whether you can get the correct answer for that.